Today we will do some exercise about the subprogram. In here we have a question. The value in high enable in port 3 is unknown. We have a value, it comes from port 3 and we will consider the high enable of it. There is 10 decimal in the low enable of port 3. When the button BT1 is pressed, multiply with 2, the value of low nibble, which is got from port 3. And when BT2 button is pressed, multiply with 2, the value of low nibble, which is got from port 3. Show the result in port 2. Okay, we have this kind of question. How can we do this question without subprogram? First of all, we will do it and then we'll use subprogram, and you can easily understand the difference between using subprogram or not. Okay, first of all, we have to get the value of low nibble of the port 3. To do A, for example. Yes, we get the port 3 value A, but in the question we know this, the high nibble is unknown and we will consider only the low nibble of the port 3. So what will we do now for the information in A? Okay, we have to do a masking operation for the information in A, because we will not consider the high nibble of the port 3. So we can use A and L for it. A and L A 0 0 0 0 1 1 1 1. So if we do this operation, then we get only low nibble of the port 3 to the A. Okay, now we have information. What is the other operation? When button 1 is pressed, multiply with 2, but if the button 2 is pressed, multiply with 3. In here it is not 2, it should be 3, sorry. Okay, it should be 3. So we have to check the button. How can we check the button value? When it is pressed, what is the value of button? How can we understand, or how can we accept the value of the button is pressed or not? We can use jump if bit or jump if not bit. We can easily understand the button value with the figure in here. When you press the button, the value of pin will be ground. It means 0. So if it is not pressed, the value of pin will be 1. Okay. So if you check the button value, which command will be used? Assume that you use jump if bit. What is the operation for jump if bit? If the bit value is 1, condition is satisfied. But in this question, we have to check bit value is 0, right? Because it is pressed. If it is pressed, the pin value will be 0. So we have to use jump if not bit. Jump if not bit, port 1.0 multiply with 2. If it is not satisfied, the program will continue with the next command. So here we have to check port 1.1, right? How? We have to use again the same command to check the button 2. Jump if not bit port 1.1, and if it is satisfied, multiply with 3. Okay, if it is not satisfied, what will be happen? What we want from the program? The polling operation will be continue, right? How? We can branch to the program as like that, and x1 should be here, of course. We check the port 1.0 and then we check the port 1.1. If the two of them, both of them are not satisfied, so the program will continue with the next line, but we have to check again and again. So the program will continue to the x1. But if the condition is satisfied, we have a new two, as you see, two label. So we have to do this label. Multiply with 2. How can we do this operation? We can use rotate left because the operation is only multiply with 2. We can also use multiplication mul command, but here, as I said before, if you do the same operation with rotate left, so you can gain a time for executing the program. So we have to use here rotate left command. Rotate left A. Now we have multiply with 2 value in A, and we have to send this value to the where port 2. Move port 2 A. And then we have another operation here. No, we can return to the same operation again. Sjump, where if the low nibble of the port 3 will be changed, we can get the new value of port 3. So we have to go X. And then the other label is here, multiply with 3. We have to do this operation. For it, we have to use multiplication command. So first of all, we have to get B value. It is 3D, and multiplication A and B, and the result will be sent to the port 3. And we don't have any other operation. We should go to the line 3, which is X, sjump X. For this program, do we need any infinite loop? No, we don't need to write infinite loop because the same operation will be continue. As you see, sjump X mean the new value of low nibble port 3 will be obtained. It is masked, and we will check the button value, and the program will continue as like that, and then it will turn back to the X, and it is continue as like that. So the program will not meet end directive. We don't need to write also infinite loop for this program. Okay, maybe we can check it is true or not. We have no error and no warning. Let's try it in the debug session part. We need port 1 and port 2, right? We don't need port 0, port 1. Yes. In the question, assume that the low nibble of the port 3 is 10D. Let's do it together. The low nibble is A. It's mean 10D. Okay. But port 3, sorry. We have to get port 3 here. Yes, port 3. 10D. High nibble is not important for us. We will consider only low nibble. Okay, then we can continue to execute the program. We are in line 2. We get the port 3 value, which is FA. As you see here, we will do masking operation for the high nibble, and the new value of A will be 0A. Yes, we will check the button value, port 1.0 and port 1.1. As you see here, both of them is logic 1, so the condition will not satisfied and the program will continue with the next line. And it is also not satisfied, so the program will continue to the sjump x1 again and again with this 3 line. Let's try it. Yes, it is not satisfied, and the program will turn back to the line 5. It will continue as the same way. But assume that we will press to the button to port 1.1. So now this condition will be satisfied. Program will go to the mul3 label, line 12. Let's try it. Yes, we are in here. The value of A is 0A. Maybe we can check it with the calculator. Yes, we have A value and we will multiply with 3. Then A value will be 1E. Okay, the result will be 1E. We checked it. Let's do this. Multiplication with B. B is 3 and A is 1E, as you see. And the result should send to the port 2. And port 2 is, as you see here, 1E now. And go back to the sjump X. We are in the same line. Now we can check the button 1. When we press the button 1.0, what will be happen? This condition will be satisfied and program will continue from line 9. Yes, the value of A times with 2, what will be happen? Times with 2, the new value or result will be 14 hex. Let's try it. Yes, A is 14 hex and the value of A will be sent to the port to 14 hex, and the program will continue and repeat itself. We saw before EQ directive. In here, can we use EQ directive for the bit-based operation? Let's try it. Port 1.0, beta 1 EQ, port 1.0, and BT2 EQ, port 1.1. Let's try it before. Yes, it can be possible. So here we can use BT1 and here BT2. Okay, it is the same operation. We can try again. 3. Let's try it. Yes, A is FF. We can get port 3, sorry. Assume that the value, the low nibble of the port 3 is 3, masking the high nibble, and we'll check the button 1 and button 2. When we press button 1, for example, we will multiply with 2. The low nibble of port 3 is 3 times with 2, it will be 6 decimal and sent to the port 2. It is the same with the old version of the question. Okay. How it is possible for this question? How can we modify this question to the subprogram? Because in here, perform the above multiplication processing in the subprogram. In the first program, multiply with 2. In the second program, subprogram, multiply with 3. How can we do it? Do you have an idea? We can already check the button value in here, and if this condition is satisfied, program will branch to this line. So, if I write here equal times 2, for example, the program will go to the related line. So this operation will be done in the subprogram. Where is the times 2? We can write here times 2, and the operation is as like that. For the quit subprogram, here we shall use ret command to quit the subprogram. When the program is met with the ret, we'll continue from the next command after the equal command, sjump x, and program will go back to the line 5. In the same way, we can use here another subprogram equal times 3 or times 3, and the related subprogram should be here. And quit the subprogram. That's all. That's all. If this line is satisfied, program will go to the line 10 and will call the subprogram times with 2. And in the times with 2, we will do related operation, and ret command will quit the subprogram. And program will continue with the next command, which is sjump x here. So program will go back to the line 5. And for the multiplication with 3, we used another subprogram command, and it is the same with the times with 2. When you compile this program, we have no error and no warning. Let's go to the debug session part and assume the port 3 value again, maybe 1. Okay, we can choose 1. Yes, continue. All of them the same in here until line 11. Assume that we will do times with 2. What will be happen now? We can also check the program counter value and stack pointer value, and also the related address value. What will be happen? First of all, we can analyze it. In here, A is F1. Okay, and then here 01 hex, of course. Okay, this condition is satisfied. What will be happen? Program will go to the line 11 because we pressed the port 1.0 BT1. Okay, we are in here and we have a subprogram command. What will be happen now? The program counter value for the next command should be stored in the address pointed by stack pointer. Okay, we can easily see the program counter value from this window. Equal times with 2 and the other command, next command is sjump x. As you see here, the address value of the sjump x is 0010. Okay, so here PC value will be 0010 hex. And what about the other? Stack pointer will be increased by 1. Stack pointer will be 08 hex, and then 08 hex address will be get low nibble of the program count 10 hex, and then stack pointer increased by 1 again, and 09 hex address will be 00 hex, which is high nibble of the program counter, high byte of the program counter. And then the last operation, when we call the subprogram, program counter will be changed according to the label. Where is the label? Times with 2 here. Maybe we should check it in here. Times with 3. Yes, times with 2. Yes, the first command in the subprogram is rotate left, and the address value in the program memory is 0016. Okay, so the program counter value 0016 hex. Okay, so program will go to the here 0016 hex, and we'll do this operation. When we met red command in here, what will be happen? Returning address should be obtained from the address pointed by stack pointer. So program counter high value is, what is the stack pointer value? 09 hex. The last value of it is, maybe we can write here stack pointer 09 hex, and what is the value? 00 hex. 00 hex. It is the high byte of the returning address. And program counter low value, stack pointer value decreased by 1, 08 hex, and it is 10 hex as I remembered. Maybe we can check it. Yes, 10 hex. And stack pointer value, the last value of the stack pointer decreased by 1, it's mean 07 hex. That's all. Okay, let's check it. Stack pointer, the default value of the stack pointer is 07 hex. In line 6, program counter value is 4 hex. Let's continue from here. Yes, we are in line 7 and the condition is satisfied because of the port 1.0. Go to the line 11. We are in here, stack pointer now 07 hex. When we execute this command, all of this operation will be happen. Let's check it. Yes, the last value of the stack pointer is 09 hex. Okay, as we expect. What is the 08 hex and 09 hex address? We can check it here. 08 hex is 10 hex and 09 hex is 00. What is the program counter value? Yes, we can check it from here. Program counter value is 16 hex. So program will continue from line 17. We will do this operation, and when we match red command, all of this operation will be done. Okay, let's execute it. Yes, stack pointer return back to the 07 hex, and program will go back to the 12. It's mean program counter high value and program counter low value is extracted to the PC from the address value, related address value. Okay, in this program, let's try some program crash. Okay, in here, if we write move set bit RS0. What does it mean RS0? Move R1 10x. It's mean set bit RS0, the low bits or the bank selecting bits is set now. Bank 1 is selected here. Okay, if I modify this program with these two lines, what will be happen? What do you think? Program will crash. Why? What does mean R1? In the bank 1, we select the bank 1 and we wrote a value to the R1. Where is R1 in the RAM for bank 1? 09 hex, as I remember. The new value of 09 hex is 10 hex. Actually, it should be 00 hex. Right? It should be 00 hex, but it is changed now 10 hex. So when we match with the red command, program will crash because it is not go back to the related line 12. Let's try it. We have no error, no warning, and we can go to the debug session part. And where is the program crash command? Multiply with 2. Okay, so we have to press button 1. Let's try the program. Get the port 3 value and we will do some masking operation and echo times 2. As you see, from 08 hex and 09 hex, the returning address will be stored in this memory cell. We will do the related operation and set bit RS0. Now we will use bank 1 you can check from the program status word. RS1 means bank 1 is used. Okay, when we click this line, R1 will be 10 hex. R1 will be 10 hex. It is mean 09 hex also be 10 hex. Let's try it. Yes, R1 is 10 hex, 09 is 10 hex, but in this memory cell we have, unfortunately, we have returning address. Program will continue from 1010 hex, but the related memory area 1010 hex, 10 and 10, we have no any comments. In 1010 hex address we have no other comments, so program will now go back to the related line. Let's check it. Yes, access violation, permission error here. Program will not continue as you see here. Okay, we have two other command, push and pop commands. Maybe we can try this command, move 10 hex 30 hex value. If we use push command, push 10 hex, the value of 10 hex will be loaded to the address pointed by stack pointer. And we will do other operation, rotate left 10 hex, we cannot use just like that, sorry. Maybe we can get to the A, 10 hex, rotate left A, it is not important. And then assume that we want to get the value of the 10 hex again, pop, where we want to get to the 20 hex address. That's all. Finish with the infinite loop because it is needed in this program, x1 and sjump x1. Okay, when we compile this program, let's try it in the debug session part. Yes, we are in line 4. Yes, stack pointer is 7 hex as you see. 10 hex value will be 30 hex. We can check it from the memory address window. 10 hex address has 30 hex value. When we use push 10 hex command, what will be happen? What is the stack pointer value? 07 hex. First of all, it is increased by 1. The stack pointer will be 08 hex, and in this address we will store a value which is 30 hex. That's all. And we have other operation, it is not important. When we execute this line, first of all we will get the value to the 20 hex address. 20 hex address will be 30 hex, and then stack pointer value will be decreased by 1, 07 hex. Let's check it now. We are in line 6, push 10 hex. Yes, when we click push 10 hex, we should see the value of 08 hex. As you see here, stack pointer is 08 hex, the new value it. So when we write 08 hex here, yes, the related address has 30 hex value now. We have other operation here, not important for us. Yes, here when we click this command, when we execute this line, 20 hex address will be 30 hex and stack pointer go back to the 07 hex. Let's try it. Yes, stack pointer go back to the 07 hex. What about the 20 hex address? Maybe we can write easily to easily see value. Yes, 20 hex address value is 30 hex. Now push and pop command can be used as like that. We are in subprogram and let's modify it in here. If we use push 07 hex, for example, and before the quit or the alt program, if we use pop command, for example, 20 hex, we don't need to, we will not any problem about the program crash. Let's try it. Yes, assume x1, where is x1? Yes, we have to x1 label. Yes, no error, no warning. Let's try it. BT1 is pressed and program will continue. Now we will go to the subprogram. Yes, we are in subprogram. Until this line, the stack pointer value is 09 hex. If we click executing this line, stack pointer will be 0A hex. 0A hex. And 0A hex, we have a value which comes from 08 hex. It should be 0, I think. Maybe we can check it. Yes, 07 hex, we have 0 value. So 0A hex address will also be 0. And when we get this value to the 20 hex, this address also be 00 hex. Yes, here we expect that stack pointer will be 0A hex, and here it will be again 09 hex. So we have no problem about the subprogram. Yes, stack pointer is 0A hex and stack pointer is again 09 hex. So the program will continue with the correct line as jump X.